A car dealer has warehouses in Millville and Trenton and dealerships in Camden and Atlantic City. Every car that is sold at the dealerships must be delivered from one of the warehouses. On a certain day, the Camden dealers sell 10 cars and the Atlantic City dealers sell 12. The Millville warehouse has 15 cars available and the Trenton warehouse has 10. The cost of shipping one car is $50 from Millville to Camden, $40 from Millville to Atlantic City, $60 from Trenton to Camden, and $55 from Trenton to Atlantic City. How many cars should be moved from each warehouse to each dealership to fill the orders at minimum cost? So to solve this, let's just first draw a diagram so that we can understand what's going on here. So we've got warehouses in Millville and Trenton. And we've got dealerships in Camden and Atlantic City. Now we can send cars from Trenton to either of those dealerships or from Millville to either of those dealerships. We know that Millville has 15 cars available and Trenton has 10 cars available. Furthermore, we know that Camden needs 10 cars, and Atlantic City needs 12. Okay. So all the information that's given here, we need to kind of make sense of it using some variables. So what we're going to do is let x be the number of cars from, we'll say from Millville to Camden. Okay, so that's this arrow right here. That's x right there. Now we want to make sure we're not using too many variables. So notice that if we know there's x cars going from Millville to Camden, and Camden only needs 10 cars, then what's going from Trenton to Camden is going to be 10 minus x. Okay, so for example, if there's 3 cars going from Millville to Camden, we know 7 will be going from Trenton to Camden because we need, we need 10 cars there. Okay, and then we can let y be the number of cars going from, and we'll stay with our Millville, from Millville to Atlantic City. Okay, and so that's y right here. And then using similar reasoning, okay, as over here, Atlantic City needs 12, and so if y are coming from Millville, then 12 minus y are coming from Trenton. All right, so those are our variables here, and now we're ready to start talking about some inequalities. Okay, first of all, x and y represent number of cars that are going, so x has to be greater than or equal to 0, and y has to be greater than or equal to 0. But also 10 minus x has to be greater than or equal to 0. Okay, in other words, well, I'll just write it like that. 10 minus x has to be greater than or equal to 0. And 12 minus y has to be greater than or equal to 0. And taking each of these, we can actually get x and y by themselves. So this one tells us that x has to be less than or equal to 10. And this one tells us that y has to be less than or equal to 12. All right, so we've got here just some basic restrictions on what x and y can be. But then we also know that we need to look at the fact that Millville only has 15 cars. So the total number coming from Millville cannot exceed 15. So that means that x plus y has to be less than or equal to 15. And then similarly for Trenton, okay, 10 minus x plus 12 minus y has to be less than or equal to 10. All right, so there's a lot of inequalities going on here, but that's the set that we have. And now we're ready to look at our objective function. Okay, this is the thing that we're trying to maximize or minimize. And in this case, it's cost. We want to minimize the cost. So the cost of shipping a car is $50 from Millville to Camden. That's this X. So 50 times X. Okay. And then we've got $40 from Millville to Atlantic City. That's Y. So 40Y. And then plus, we've got 60 from Trenton to Camden. That's this 10 minus X. So plus 60 times 10 minus X. And then finally 55 from Trenton to Atlantic City. So that's the 12 minus Y. So 55 times 12 minus Y. We can simplify this quite a bit by just expanding and combining our like terms. So let's go ahead and do that. We've got those, and then distributing the 60, we have plus 600 minus 60x, and then plus 660 minus 55y. All right, so combining our x terms, we've got negative 10x. And combining our y terms, we have a negative 15y. And then we've got our constant terms, 600 plus 660, that's 1260. So this here is our cost function. And that is what we're trying to minimize. Okay, and it's subject to these 6 constraints. So now we're going to go ahead and look at the feasible region here. So here's our feasible region with our vertices labeled. And we are trying to minimize the cost. So all we need to do now is plug these 4 points into the cost and see which one gives us the smallest cost. So we have the point 0, 12 that we're going to plug in, and 3, 12, 10, 5, and 10, 2. And I'm going to go ahead and assume that you're good just plugging numbers in and seeing what you get. So I'm going to go ahead and speed this up. And now just looking through these different costs, we see that the lowest cost was right here at 3 and 12. And so that's the x and the y. And so what this tells us, if we just go back and look again at what x and y meant, that means we'd have 3 going from Millville to Camden and 12 going from Millville to Atlantic City, and then 7 from Trenton to Camden, and none from Trenton to Atlantic City.